In this video, we're going to discuss the proof of the theorem of mathematical induction. So the theorem of induction justifies proof by induction. It's a little unusual in the sense that it's a proof technique that we prove is a valid proof technique. So the theorem of induction states as follows: let P of n be a statement that's either true or false, but not both, for each natural number n. Now, if the statement is true for n equals 1, so if P of 1 is true, and if whenever P of n is true for some natural number n naught, then P of n is true for the successor n naught plus 1. If those two things are true, then the statement P of n is true for all natural numbers n. That's our theorem of induction. Our proof of the theorem of induction is going to rely on a couple of the basic properties of the natural numbers. So the properties of the natural numbers that we'll use include the subtraction property, which states that if n is less than m, then there's a natural number k such that m is equal to n plus k, so k would be the difference between m and n. And the well-ordering principle, which states that every non-empty set of natural numbers has a minimum element. And it'll be important to the proof that we remember the definition of the minimum of a set. So recall that if A is a set, then M is a minimum of A if M is an element of the set A, and for any other element x in A, M is less than or equal to x. Okay, so again, let's state the theorem of induction before we prove it. So let P of n be a statement that's either true or false, but not both, for each natural number n. If the following statements are true: 1, P of n is true for n equals 1, and 2, if P of n is true for n equals n naught, then P of n is true for n equals n naught plus 1. If those two statements are true, then P of n is true for all natural numbers n. So let's get into the proof of this. We'll start the proof by assuming that P of n is some statement that's either true or false, but not both, for each natural number n. We'll assume the assumptions of the hypotheses of the theorem of induction. We'll assume that the following statements are true. We'll assume that P of n is true for n equals 1. So we're assuming that P of 1 is true. And we'll also assume that whenever P of n is true for some natural number n naught, then P of n is true for the successor of n naught. It's true for n naught plus 1. Okay? So we're assuming that P of n is true for 1, and we're assuming that whenever it's true for one natural number, it's true for the next natural number. So our proof will rely on the well-ordering principle, and we want to apply the well-ordering principle to the following set. So we're going to construct this set A, which is the set of all natural numbers, so that P of k is false. So it's a set of all natural numbers k, so that P of k is false. Now this set is either empty or it's not empty. We don't know which at this point. But it does give us two cases to consider. So first we'll consider the case where A is not empty, and then we'll consider the case where A is empty. So suppose that this set A is not empty. In other words, let's suppose that the set of all natural numbers k, so that P of k is false, is not empty. There's something in that set. Well, if there's something in that set, then A is a non-empty set of natural numbers. And now we can pull out the well-ordering principle, and implies here that A has a minimum element, which we'll call m. So again, recall the definition of the minimum element. So if m is the minimum of A, then we know that m is a member of the set A, and we know that if x is a member of the set A, then m is less than or equal to x. Okay. Before we continue with the proof, though, we're going to restate the second property. We're going to restate this second property of being a minimum. Instead of saying that if x is in A, then m is below x, we'll say that if x is below the minimum, then it can't be in A. Okay? So if x is below the smallest thing in A, then we know x is not in A. So we're going to use that reformulation of the second criteria for being a minimum. But before we do that, let's recall our assumptions in the proof. So we're assuming that, firstly, P is true for n equals 1, so P of 1 is true. And we're assuming that if P is true for n naught, then P is true for n naught plus 1. So we're assuming that P of 1 is true. That means that 1 cannot be a member of the set A. Because remember, A is the set of all natural numbers for which P is false. Okay, but one of our assumptions is that P is true for 1. So we know 1 is not in the set A. Alright, well that tells us something about the minimum of A. Okay, in particular it tells us that the minimum is not equal to 1. The minimum is in the set A, 1 is not in the set A, so m can't be equal to 1. And 1 of course is the smallest natural number, so if m is not equal to 1, it must be strictly larger than 1. So we have that 1 is less than m, and now we'll apply the subtraction property of the natural numbers to find a natural number s so that m is equal to 1 plus s. Okay, but let's think about s now. S is smaller than the minimum. S is smaller than m. So if we use our reformulated second criteria for being a minimum, we know that since s is smaller than the minimum of A, it cannot be a member of A. So s is not a member of A. Okay, but think about what that means. S is not a member of the set of natural numbers for which P is false. Okay, S is not in that set. That means that P is not false for S. In other words, P of S is not false. Well, if P of S is not false, that means that P of S is true. Okay, so that's important because now we're going to apply the second assumption of our proof. Remember, our second assumption was that if P of n is true for one natural number, then it's true for the immediate next natural number. Okay, and by saying that S is not in the set A, we infer from that that P of S is true. Well, that's got to mean that, by our second assumption, that P of S plus 1 is true. Okay, so again, P of S is true, and one of our assumptions in the proof is that if P is true for one natural number, it's true for the next natural number. So that means that P of S plus 1 must be true. Okay, well that's going to get us into some trouble because S plus 1 is equal to M. S plus 1 is the minimum. So that implies then that P of M is true. Okay, but of course M is the minimum of A. It's in the set A. So that means that P of M has to be false, right? So we have a problem here. Our assumption that A is not empty leads to a contradiction. It, on the one hand, implies that P of M is true, and on the other hand implies that P of M is false. Okay, so we have a contradiction from our assumption that A is not empty, and that means that this case can't occur, that we have to rule out this case. Okay, and so this case cannot occur. A cannot be non-empty. In other words, A has to be empty. So let's look at that. So now let's turn to the case where A is empty. First of all, we know it has to be empty, so this is a valid assumption. And what it means is that if n is a natural number, then n is not in the set A. Okay, so if n is a natural number, then P of n is not false. If n is a natural number, then P of n is not false. Well, that exactly means that for all natural numbers n, P of n is true. And that's what we wanted to prove. That's our conclusion of the proof of the theorem of mathematical induction. Thanks for listening.